Right. Okay. In the last class, this is a place where we stopped. We were looking at how to evaluate stability, right? And then we were what to say? We learned that if I want to essentially evaluate the stability of any system in the class of systems that we are studying, so we need to look at the closed loop poles, right? In essence, if I am given any transfer function, if I want to comment on the stability of the system, which essentially corresponds to the transfer function, I need to look at the denominator polynomial of the transfer function, and all the roots of the denominator polynomial must be in the left of complex plane, right? So that's the criteria for Bibo stability, right? So we asked ourselves the question, if we have any system, any generic system, right? So how do we essentially figure out, when that system would be Bibo stable? And why did we ask ourselves this question, right? So we were doing some problems, right? So where we encountered this scenario, right? So I gave you a problem to do for the Planck transfer function being 1 by s squared plus 1. We saw that that has a couple of poles on the imaginary axis at plus or minus j. So obviously, as we know, if we give an input like cos t or sin t, the output is going to become unbounded. So we wanted to design a unity negative feedback system, and we tried with the proportional controller, and the proportional controller couldn't help us there, right? So then we tried the PI controller, but then when we tried the PI controller, we ended up with a third order polynomial, right? So now the question becomes, I have two parameters that I can change, and I have a third order polynomial. Can I find out conditions that would ensure that for at least certain ranges of values of these parameters, the closed loop poles would lie in the left of complex plane, right? So that's the question we ask ourselves, right? So that led to a general question, right? So on when would a polynomial be Hurwitz, right? So so essentially we consider a polynomial d of s, which is a naught s power n plus a1 s power n minus 1 all the way till an, okay, where all the coefficients a naught, a1, a2 all the way till an are all real numbers, right? So this polynomial is said to be Hurwitz if all its roots have negative real parts, okay, that's the definition of the term, okay. So why is it connected to our discussion? Because if I am designing, let's say, a control system, I look at the closed loop transfer function, I want the closed loop characteristic polynomial, right? So which is the denominator polynomial of the closed loop transfer function to be Hurwitz, right? So then I am assured that my closed loop system is going to be stable, correct? So so that's what we want to answer. So the question that we stopped with last time was, we asked ourselves the question, how do we evaluate whether a given polynomial d of s is going to be Hurwitz, right? So this is the question we asked ourselves, okay? So let's continue from there, right? So let's first consider a first order polynomial, right? So let's say we consider n to be equal to 1. Okay, so I have the polynomial to be a naught s plus a1. So when do you think this polynomial would be Hurwitz? Yeah, so you see that this would be Hurwitz when a naught is not equal to 0, a1 is not equal to 0, and both a naught and a1 have the same sign, right? So they can both be positive or both be negative. Anyway, in this case it's pretty simple because the root is going to be just minus a1 by a naught, right? So that's the root of this polynomial, first order polynomial. So the answer is pretty straightforward, right? So if I want this real root, to be negative, then this is what I want, right? So essentially I want both the real numbers to be of the same sign, okay? So that's for n equals 1. So now let's do n equals 2. So let's say now my polynomial d of s is a naught s squared plus a1s plus a2, right. That's my second order polynomial. Now the question is that we ask ourselves the same question, right. When do you think this polynomial would be Hurwitz? So this is a second order polynomial, right. So I need to solve the quadratic equation a naught s squared plus a1s plus a2, right. So when do you think this polynomial would be Hurwitz? So it so turns out that this polynomial would be Hurwitz when a naught, a1 and a2 are first of all non-zero, okay, and of the same sign, okay. Once again the same criteria, okay. So you apply it to any quadratic polynomial. So if all the coefficients are non-zero and of the same sign, we are done, right. We know for sure even without calculating the roots, right. So we know that the roots are going to be in the left of complex plane, okay. See, please note that we are interested to begin with the question of locating the roots, okay. So I am only asking myself the question whether the roots are in the left of complex plane, the imaginary axis, or on the right of plane, right. We are not looking at the exact locations right now, okay. I am only looking at the half plane, okay, whether all my roots are going to be the left of complex plane, okay. So that's the question we are asking ourselves. Then we will come to the exact locations, okay, that we would come later, right. So even without calculating for the roots, you know, like if a naught, a1, a2 are non-zero and of the same sign, I am assured. So that you know, like the two roots are going to be of the same sign. Two roots are going to be in the left of complex plane, okay. That's assured for the second order polynomial, okay. Yeah. So now what happens when we go to a higher order polynomial, okay. That's what we are going to do. So now let's go to n equals 3. So now the polynomial becomes a naught s cube plus a1 s squared plus a2 s plus a3, okay. So now there are 4 coefficients. Please remember, you know, the way we have written it, for an nth order polynomial we are going to have n plus 1 coefficient, okay. See, in any general nth order polynomial, if this coefficient a naught is 1, that's called as a monic polynomial, okay. So that means that the coefficient of the highest order term is 1. So if a naught is 1, that means that it's called as what is called as a monic polynomial, okay. So anyway, that's just for your information, okay. Oops, what happened? Okay. So that's just an aside, right. So yeah, okay. So anyway, we are going to be looking at general polynomials, okay. So for an nth order polynomial, we are going to have n plus 1 coefficients, as we can see. Now the question we ask us the same question, right. So what happens in this scenario, right. So do we still need a naught, a1, a2, a3 to be non-zero and of the same sign? Yes, we do. But it so turns out that for polynomials of order 3 and more, that is only a necessary condition, okay. It is not sufficient. So what do I mean by that? You know, like, yes, for all the 3 roots to be in the left of complex plane, I need the coefficients to be non-zero and of the same sign. But it so turns out that that necessary condition is also sufficient for polynomials of order 1 and 2, but not so for polynomials of order 3 and more, okay. So let me demonstrate it to you through 2 examples, okay. So let's consider a couple of examples, okay. So let's say we consider the first polynomial to be s cube plus 3s squared plus 3s plus 2, okay. So that is the first polynomial we have. Does anyone have a scientific calculator and you can calculate the roots and let me know? Can you calculate the roots of this third order polynomial? okay. And then what we do is that, like, we consider a second example where D2S is going to be SQ plus 2, I'm sorry about that, you know, like, kindly let's change the numbers. And the first polynomial, it's going to be SQ plus 2S squared plus 3S plus 1, okay. In the second polynomial, the polynomial is going to be SQ plus 2S squared plus S plus 3, okay. So can you tell me what are the roots of D1 and D2? What can you observe as far as the first example is concerned? Of course, both have 3 roots, right? It's a third order polynomial, right? Both D1 and D2 are third order polynomials, right? You have 3 roots. What can you say about the 3 roots of D1? All have negative real parts, okay. So then what can you say about D2? Okay. So one negative real root and 2 roots in the right of complex plane, right? I am only looking at the location right now, okay. So right now, you know, like, please, I want all of you to go and do this, okay. You can use MATLAB also to easily figure it out, okay. In MATLAB, if you use the command roots, okay, you will get the roots of any polynomial, right? So that's the command in MATLAB. So for example, in the command line, if you type roots of 1, 2, 3, 1, right? So you will get the 3 roots of the first polynomial and so on, right? So please get the exact location, but then right now I am only looking at the location. All 3 roots are in LHP, right? The left of complex plane in first polynomial, while here, 1 root in LHP and 2 roots in RHP. Now, what is the only change I did between D1 and D2? We just swapped or interchanged the coefficient of the S power 1 term and the constant term, right? We did not do anything else, right? But then you see a drastic change in the way the roots of the 2 polynomials are distributed, right? So imagine that, you know, like, D1S is the denominator polynomial of a transfer function that, let's say, one of you design, and D2S is the denominator polynomial of a system that I designed, right? So the one that I designed would be unstable, isn't it, right? So the question is, then how do I figure out the location of roots of polynomials of order 3 and more, right? Because we immediately see that what was necessary and sufficient for polynomials till order 2 is not sufficient here, okay. So although we are not proving that, you know, like, so, but you can take it as a fact. So all in these 2 polynomials, all coefficients were non-zero, all coefficients were of the same sign, right? I am sure all of us can agree to those points, right? But still you can see that there is a difference, right? Then how do we, essentially figure things out, right? So let's write down the general condition, but I hope everyone is, understanding the flow of our discussion, right? Where we are headed, right? So it so turns out that for polynomials of order 3 and more, a necessary condition for them to be Hurwitz is that all coefficients must be non-zero and of the same sign. Okay, that's a necessary and well, that's just a necessary condition, okay, for polynomials of order 3 and more. We can immediately see that, right? So you can see that D1 and D2 both satisfy the necessary condition, right? But that's not sufficient. Okay, so I hope this further illustrates the difference between necessary and sufficient condition, right? Suppose, let us say, like, I am just considering a simple example where, let's say I have D3 of s to be s cube plus 2s squared plus 3s. Okay, what did I do? I took D1 of s, made the constant term to be 0. So does it satisfy the necessary condition? No. So what are the roots? You can immediately compute. You can take s common, and this is what you have. So although 2 roots will be in the left of complex plane, you have a root at the origin. Gone, right? So you see that once you violate the necessary condition, you can immediately conclude that not all roots will be in the left of complex plane. Okay, so that's the importance of necessary conditions in general, right? So if the necessary condition is not true, you can immediately stop, right? So you immediately say that the or the statement that you are starting off with, or the hypothesis which you are testing is not true. Okay, but this is not sufficient, as we have seen from the above example, right? We need something more. What is that something more? Okay, that's what we are going to learn now. Okay, so what is that something more? Like for sufficiency, we construct the routes array. Okay, so that's what we are going to do. Okay, that's the process to figure out sufficiency, right? So what is this routes array? Okay, so let me construct the routes array, then we will discuss the implications for us, right? So okay, so let me write down the routes array. So what we do is that when I want to construct the routes array, first what we do is the following, right? So I write s power n minus 1, s power n minus 2, s power n minus 3, like that, right? So whatever coefficients I have, s squared, s power 1, s power 0. Okay, so I just write down all the coefficients of s, sorry, or not coefficients, all the powers of s as a column. Okay, that's what I do as a first step. Then what I do is that I start filling in the first 2 rows of this array, that is the s power n and s power n minus 1 array, rows, with the coefficients of the polynomial which I am given. Okay, in the same sequence. Okay, in the order of the decreasing powers. So essentially we start with a naught, because please remember the polynomial which we are considering is a naught s power 1, a n s power minus 1, all the way till a n minus 1 s and a n, right? So we start with a naught, which is the highest power, which is the coefficient corresponding to the highest power, s power n, right? So a naught is followed by a1, then the coefficient of s power n minus 2 is a2. I don't write it here, but then I go here and write it as a2, then a3, a4, a5, a6, a7 and so on, right? So I keep on going till I get exhausted, right? So I stop with the coefficients. Okay, so that's what we do. Okay, that's step number 1. Is it clear? Okay, so that's what we do to begin with. Then what I do is that I start calculating. Okay, so I start calculating coefficients like b1, b2, b3, c1, c2, c3, like that. Okay, and then I keep on filling in the coefficients of the routes array. Okay, now the question is like, how do I fill these coefficients, b1 and b1, c1s and so on, right? bi's and cs. Okay, so let's come to b1. So if I want to calculate the coefficient b1, for that matter any coefficient in any row, I consider the coefficients which are available in the 2 rows that are immediately above that row. Okay, in this case b1 appears in the s power n minus 2 row, right? So I consider the 2 rows immediately above that, okay, which are essentially s power 1 and s power n and s power n minus 1. So to find b1, what I do is that, once again, like I am not proving this, I am only stating the result to you, okay. B1 is going to be equal to A1 times A2 minus A0 A3 divided by A1. So how do we do this, right? So let me demonstrate to you. So what I do is that, like, I multiply A1 and A2 and subtract from that the product of A0 and A3 and divide by A1. Okay, so that's what we do to get B1. Okay. Similarly, if I want to figure out B2, what I do is that I multiply A1 with A4, subtract A0 with A5 and divided by A1. So for all entries in the S power n minus 2 row, this A0 and A1 will be common, okay, and A1 will appear in the denominator. That's standard. But then the elements with which you multiply are just one column to the right. See, for example, for B1, what did we do? We multiplied, we chose A2 and A3 for B1, right? Now for B2, what we do is that we choose A4 and A5, which is just one column shifted to the right, okay, the two rows above that, okay. So what I do is that I multiply A1 with A4, A0 with A5 and then divide by A1, okay. I continue this process till I stop in the S power n minus 2 row, okay. So that's what we do. Now we come to the S power n minus 3 row, okay. I want to calculate C1, C2 and so on, right. So if I want to calculate C1, what should I do? If I follow the same process, first I will choose the two rows which are immediately above S power n minus 3, right, which are the S power n minus 1 and S power n minus 2 row. Okay, so if I want to look at C1, what do? Same process, right? I look at the two rows above it. You can immediately, figure out the pattern, right? So it's going to be B1 times A3 minus A1 times B2 divided by B1. Then C2 is going to be what? B1 times A5 minus A1 times B3 divided by B1, right? This process continues, okay. So you continue this process until you finish constructing the routes array, okay. So that's what we are going to do. Now once we finish this process, what do? We look at the first column of the routes array. Okay, this is the first column, and the sufficiency condition is that there should not be any sign changes in the first column of the routes array. Okay, that is when the polynomial would be Hurwitz. Okay, so let me write down what I just stated. So the sufficiency or the sufficient condition is that the number of sign changes in the first column of the routes array should be 0. Okay, that is the sufficiency condition. Okay. So, so please note that for any general polynomial of order n with real coefficients, right? So the necessary condition is that all the coefficient must be non-zero and of the same sign. The sufficient condition is that the first column of the routes array, once you construct it, should not have any sign changes. Okay, and it so happens that for polynomials of order 1 and 2, the necessary condition is also sufficient. Okay, we will shortly see that, right? So, but for polynomials of order 3 and more, we should check the routes array, right? So let's now apply the routes array to the two polynomials. Okay, but before we go there, note suppose if there is a sign change, right, what do we interpret from that? Okay, so what do I mean by a sign change? Let's say you start off with all positive numbers in the first column, suddenly you have a negative number, right? That's one sign change. Then from the negative number you have another positive number, that's second sign change, right? So like that. Suppose if we have a sign change, you know, like what do we interpret from that, right? So that's a question we need to ask ourselves, right? So note the number of sign changes in the first column of the rows array is equal to the number of roots of D of S, okay, in the right half complex plane. Okay, that's another result. Okay, so once again we will be using these results. Okay, as I told you, I am not proving all these results. These are well established. Okay, so
Sir, will it contain roots that are of j omega?
good question. Okay, good point. I am coming. Right. So if you have a sign change, right, then you count the number of such sign changes, and that number is going to be equal to the number of roots in the right of complex plane. Now he asked a very pertinent question, right? So I can have polynomials which are going to have roots on the j omega axis, right? How are they going to be reflected in this rows array, right? So till now I only talked about positive and negative numbers, but you can always have a 0 as a first entry, right? So if you have a 0, then we need to follow a different process, and that may imply, right, roots on the imaginary axis. Okay, we are going to test those scenarios. Okay, I'm going to come to your question maybe tomorrow. Okay, so today we will look at these examples, and then like we'll go and complete the controller example that we started off with in the last class, right? So then we'll come to some special cases tomorrow, right, as to what happens if we encounter a 0 in the first term, column, right? Then our calculation stops, right? Because see, for example, let's say B1 is 0. Let us say I do calculations and B1 is 0, then I cannot calculate C1 and C2, right? Why not? What will happen if B1 is 0, C1 and C2, they do not exist, right? So essentially, because I have B1 in the denominator, right? So when I want to calculate C1 and C2, right? So I cannot continue the process, right? Then what do we do, right? That's something which we will look at tomorrow, right? Okay. This is the rows array. So this is the rows criteria. So this criteria is what is called as the rows criteria. Okay, so these two conditions, okay, of the necessary and sufficient condition, okay, that's essentially what is called as the rows criteria. Okay, so we will anyway come back to our dynamic systems and what to say, essentially define carefully, write down what is called as rows stability criteria. Okay, but this is the rows criteria, right? So you have two conditions, necessary and sufficient.